Hi everyone, this is a walkthrough of CSM 16A Spring 2018's voltage divider question from worksheet number 6. So in this question, we're going to look at some properties of a voltage divider. So let's take a systematic look at the voltages across a resistor and see how other components in the circuit can affect it. So consider the following circuit, which is a voltage source in series with two resistors. So part A is asking to calculate the voltage drop across R1 and R2 using series resistance calculations. So we can calculate it using series resistance calculations. I'm going to do it using nodal analysis right here. So scroll down a bit. Okay, so when I say nodal analysis, I mean we're going to use KCL equations for currents and IV equations to relate voltages to each other and then solve the resultant system of equations. So first thing we do for this is we're going to label our nodes, our currents, and passive sign convention. So in here I see three nodes we can create. One node right here, U1, U2, and U3. So how I identified these nodes is I said these are all the nodes that are in between two non-wire circuit elements. So another thing we can see is we need to ground the circuit. So I choose right here. So notice that since this ground is connected to U3 by an ideal wire, that means U3 as well is at ground. So we can say right away that the potential at U3 is equal to 0. So we still don't know U1 or U2. Maybe we can see if we can get back to those with other equations. Next, what we need to do is assign currents throughout our circuit. So I'm going to say we have I1 going up from the voltage source, I2 going down through R1, and I3 going down through R2. So because I2 and I3 are going down, that means passive sign convention will have plus minus, because the current will flow from high potential to low potential through the resistors. So from that, So we have I1 flowing through the voltage source, I2 and I3 flowing through the resistors. So now let's do KCL. Since we have nodes set up and we have current set up, let's do KCL on each of these three nodes. So now for KCL equations. So for U1, we can say that I1 is going in, so sum of the currents going in is equal to sum of the currents going out. So we can say that I1 is equal to I2. Likewise for U2, sum in equals sum out. So in U2 we have I2 going in and I3 going out. So we could do U3. I'm actually going to do it right now to show an important property. In equals out. So we have I3 going in and I1 going out. So in reality, we actually do not have to do KCL at U3. It's going to result in an equation that is linearly dependent. So in general, if you have n nodes in your circuit, so in this case, if you have n nodes, in this case we have 3, you're going to have n minus 1 linearly independent KCL equations. And so in this case, we will have 2. So because of this, we do not have to use U3. I mean, I just wrote it out to show that. So this is kind of a trash equation. But from this, what's more interesting is we can see that I1, I2, and then I3 are all the same current. So you have two choices you can do here. One thing you can do is you can just choose to continue solving this with 3 separate current unknowns. What I like to do is once I notice this, I just eliminate 2 of the variables. I just choose, like, let's say I1 is the one current that remains. That is my current for the remainder of solving this problem. So because of that, I1 is going to be my only current, and actually I'm just going to call it I because 1 kind of implies that there is more than 1 current running. So in here, I'm going to just erase the unnecessary writing because all we have now is our current I flowing clockwise. Okay, so doing KCL showed that we have one current flowing through the circuit. And that should intuitively make sense because we have a simple loop. The current can't ever split or go anywhere else. All of these elements will share the same current. So that is it for KCL equations. We have two equations. Next, what I'd like to do is the IV equations. So when solving a circuit, you have a choice between using KCL or KVL, which is the sum of all the voltage changes in a loop is going to be equal to 0, or IV equations, which goes from one node to another node and calculates the change in voltage there. You can use either of those. IV is actually just, I feel like, a piecewise version of KVL. I'm going to use IV in this case. So what we're going to do is for our IV equations, let's look back up at this circuit. So let's go from the voltage source. So we know we're at ground here. So if we go up through the voltage source, we're going to be at potential V volts up here. So we can say, so V and traveling along the wire gets us to U1. So start at V minus the V wire, so the drop in voltage along the wire, gets us to U1. But the voltage across an ideal wire is always 0, so this is just 0. We can say that V is equal to U1, or that U1 is our potential V. So that's really nice. Now we only have one unknown node, so let's get some equations for that. So how about U1? How about we go from U1 to U2? So we start at U1, we go down through the resistor, so the current is traveling down through it, from plus to minus. So U1 minus VR1 is going to equal U2. We can do some substitution in here because we know from Ohm's law, V is IR. We say that U1 minus IR1 would equal U2. I didn't change anything. Yeah. So then we can go from U2 to U3 similarly. So U2 minus VR2 is U3. We can do a couple substitutions here. We can do VR2 with Ohm's law, and we can do also U3 being 0 and ground. So we can say that U2 is equal to, or not equal to, U2 minus IR2 is equal to 0. Oh, and then similarly in this equation right here for U1, I'm going to make the substitution for U1 being V. So I'm just going to do another quick algebraic manipulation here, that U2 is equal to IR2. So at this point in solving, you have two choices of what you can do to solve this circuit. A method we use most often in 16A is that you put all the unknowns on one side of the equation and just constants on the other side. You put them into a matrix and you solve. I'm going to show another way, which is substitution, which is another valid way to solve a linear system of equations. So I notice here that I have U2 isolated on one side of the equal sign, and I also have U2 isolated on this side of the equal sign. So because both of these resulting expressions are equal to U2, I can set them equal to each other. They're both equal to U2, so I can say that V minus IR1 is equal to IR2. So going from there, what was I? Oh, so from here then, I can solve for the current through the resistors, our one unknown I. Because we do know V, and we know both our R's, even though they're all symbolic. So let's solve for I. Let's put all I on the same side of the equation to isolate it. So V is going to equal IR1 plus IR2. What we can do is we can factor I out of each of the expressions. So V is equal to IR1 plus R2. So we can say single I is equal to V over I is equal to V over R1 plus R2. So now we want to find the voltage dropped across each of the resistors. We can just use in general V equals IR, Ohm's law. So for R1, V is going to equal IR. So it's going to be I times R1, which is, we solve for I over here, so it's going to be V times R1, that's over. So it's equal to the voltage source times R1 over the sum of the resistances. Likewise for R2. So there it is. This is the voltage drop across both R1 and R2. So let's move on to part B now. So part B is a slightly different situation, but we have a voltage divider in this as the common denominator. So part B reads, suppose we want to manipulate the voltage across R2, but it's locked in the box with the voltage source, as denoted below. So everything within this box right here, you cannot change. So can we use, but we can change R1, it's outside of the box. So can we use R1 to manipulate VR2? So can we change the value of R1 to change the value here, the potential right at this node? What is the range of voltages we can achieve? So an important thing for notation to notice is that VR2 is actually asking for the potential at this junction right here. It does not change anything at all that we kind of extend the wire out to here and are just asking like to measure the difference between these two terminals. Because this is an open circuit, no current will flow through here, so therefore there will be no change in voltage. So the potential right here is the exact same as the potential right there. That won't change. So using R1 to manipulate VR2. We know we solved from earlier, so we know that VR2 is what we got from the voltage divider earlier. It's going to be R2 over R1 plus R2 times V. So in this case, I like to think about what are kind of extreme values that R1 can take on. So let's say the cases where R1 is infinite resistance and when it is 0 resistance. So as it approaches infinite resistance, which is an open circuit, then this expression up here, so this expression up here is going to be V times R2 over infinity plus R2. And so this denominator will just overwhelm the numerator in all aspects, and so it's just going to be V times 0 with 0 volts. So okay, so we're going to asymptotically approach 0 volts as we have R1 take on greater and greater values. So the other case, when R1 is at 0 ohms, so this is the equivalent of a short circuit. So likewise, we recopy the equation and replace R1 with 0. V times R2 over 0 plus R2. So that's just going to be V times R2 over R2, which is V times 1, which is V volts. So we know this, so our range, so the answer is yes, we can use R1 to manipulate VR2, and the range of voltages is going to be 0 exclusive, but V volts inclusive of what we can achieve. If we want to think about this more intuitively, then if we say that R1 is equal to 0 ohms, then the proportion of the voltage that will be given to this resistor is nothing, right? So everything will be dropped across R2, so we'll get all V of the volts. It's a voltage divider. The resistors are sharing the voltage drop between them. So if we want to think about for when R1 is infinite ohms, then in that case, R1 is just going to take all of the voltage drop, and so nothing will be left essentially for R2. That's another way to think about this. So that is really it for part B. So moving on to part C. So we want to use this voltage divider now to power a light bulb with some kind of unknown resistance, where the threshold voltage for the light bulb is 6 volts. So we want to find R1 and R2 such that the voltage across R2 is the threshold voltage. So right now we're ignoring the fact that we're going to attach a light bulb to this circuit, like this, that will be in parallel with R2. Right now we are just trying to balance our circuit such that this V out is 6 volts. So any kind of resistor combo that will get that. So we know our V out is going to be 6 volts. So 6 volts is what we're trying to get. It's going to be 12 volts in times voltage divider R2 over R1 plus R2. So we have 12 over here, 6. Cross that out, 6/12. So we're trying to get some kind of combination that has R2 over R1 plus R2 equal to 1/2. So this is a pretty open-ended question, actually. There are infinite answers. As long as R1 and R2 are equal to each other, this expression will be satisfied. So there's no real answer for this question other than just R1 equals R2. If you like, you can choose numeric values for them. We can say that they're both 6 ohms, or 6 kiloohms. That's more realistic. This is one solution. One possible solution. So last question, part D. So now we have found an R1 and an R2. So I'm just going to say like they were 6 above, 6 kiloohms. We use kiloohms. 6 kiloohms for that one, 6 kiloohms for this one. That seemed to divide our voltage source appropriately. Let's try to connect the bulb to the ends of R2. And remember that the bulb has its own resistance. So calculate the voltage across R1 and R2 and the light bulb when it is connected. So actually, I'm going to solve this extremely symbolically because that is what I pre-solved. So now we have a new change, is that in this circuit, we're not ignoring the light bulb exists. We're including it as well. So I'm going to redraw the circuit. So plus minus 12 volt source. We have R1 here, and then we are going to have R2 and RL in parallel. I'm going to ground here because, as I said before, I think I like grounding below the voltage sources, and I hope you will too. So now you notice that this is slightly different than the circuit we had before. In the circuit we had before, remember, I showed in the voltage divider all the way up here, we had one single current going in a clockwise direction. In this case, we do not have one single current. Our current now, it will flow along. So it'll come out of the voltage source, be like one current and everything. It'll go here, and then it will split into 2 directions. A portion of it will go through R2, and a portion of it will go through RL. Depending on the values of R2 and RL, it will split proportionately. And you can know how it splits by analyzing a current divider for that same. Like this whole parallel combination will be a current divider. So I drew these dots. Don't want to erase the resistor though. Okay, so I is no longer like this. It is now like this. Lots of arrows, but that is how the current has changed. So this is a single loop with one current. This is a split current. So we could do nodal analysis on this new circuit once again in order to find what the new voltage right here will be at this node. We're going to be measuring this. What I'm going to do is instead use resistor equivalences, use series and parallel equivalences along with our pre-derived voltage divider equation in order to calculate what new Vout will be. So we know R2 and RL are in parallel. So there are 2 general formulas you can use for resistors in parallel. I'm going to choose the one that has multiplication in the numerator rather than the one that has the reciprocal of the reciprocals. So REQ for these 2 is equal to R2 RL over their sum. So after we've done that, we can redraw the circuit to look like this. We still have R1 up here, but now we have REQ down here. So this is great. We are back and Vout is still up here. So this is great. We are back to a voltage divider. So now using REQ instead of R2, we can solve for Vout with the voltage divider formula. So the out is going to be our 12 volts. It's still 12, yes. Or should I even use 12? Yeah, I can use 12. So it is 12 volts times our REQ. So I'm going to substitute that in right now. R2, RL, R2 plus RL. And then that is over the sum of everything. So R1 plus this fraction just smaller. I hope my handwriting's still readable at this small size. So after a bunch of simplifications, which I'm not going to copy onto here, I got that it is equal to this. 12 volts times R. Oh, okay. One thing I did substitute in as well is we knew that R1 and R2 were equal previously, so I said R1 equals R2, just equals some general R without a subscript. So I did that substitution, and then I also did some algebra to get RL over R plus 2RL. So this is our new voltage at that one point. So notice that for this expression, like no matter what our value of R is here, even if it's 0, we are always going to be we're going to always be equal to or smaller than 1/2. So this is less than or equal to 12 times 1/2, so which is equal to 6. So we are actually never going to hit 6 volts and let the light bulb turn on. So the moral of this was that you can't really pre-calculate some kind of voltage for voltage divider, hook up some extra circuit element like a light bulb and expect everything to perform the same way. It will not do that. What this is doing is it's loading the circuit. So you're loading it with this new value. Because now the current in this case, I'm going to erase the annotation, go up. So I'm going to erase the annotations. So the current in this case, it is going to come up through here, travel along. At this node, it will split. Some of it will go through R2, some of it will go through RL. So in this case, we know that the two resistors in parallel will have an equivalent resistance that is smaller than each of their individual resistances. So from intuition from before, the total voltage dropped across this new equivalent resistance will be less than before. So this goes to show that you cannot just arbitrarily load a circuit and expect it to stay the same. So in upcoming weeks, we're going to learn about using things like buffers in order to mitigate this effect. So that's the end of the voltage divider walkthrough. Thank you for watching this video.